Good morning, good afternoon, or good evening. Wherever you are in the world, welcome and thank you for joining us. My name is Carl Anthony, and this is AutoVision News live from AutoSens Detroit 2023. We are set up in the heart of the Motor City, downtown Detroit at the Huntington Place. Joining us is Daniel Shwartzberg, Director of Business Development and Systems Solutions at Valens Semiconductor. Daniel is responsible for ensuring customer success at the technical level, working with OEMs and Tier 1s globally on proofs of concepts and having those technical pre-sale discussions. Daniel brings close to 30 years of experience, predominantly within the semiconductor industry. He joins us for our AutoVision News Live program at AutoSens. Daniel, welcome.
Thank you, Carl. Great to be here again.
And it's Shwartzberg, not Schwarzenberg.
Well, it's a little bit complicated, but Schwartzberg is perfect. Yes, indeed. You're not the first one to ask that.
I got it. Well, it's great to be in person. We were just having this discussion on camera that when you're in person and you can see the technology, you can really see it in front of you. That's when it makes the most impact. So, Daniel, tell us about Valens. And then after an overview of Valens, tell us about your product range then.
Okay, so Valens is a semiconductor company. We're a fabless semiconductor company. That means we do all of the design work, but then we ship out all of the manufacturing, shall we say, the test to third parties. Since our inception, we've been focused on bringing the best wired connectivity solutions, actually to a range of markets. We began in the professional audio video market in 2006, but then towards around about 2013, 2014, we realized that the automotive industry was also suffering from issues in terms of the complexity, the cost, the weight of the wiring harness. And in fact, we brought our first generation of product, which was an adaptation of the Pro AV chipsets, which have been sold in millions and millions of products around the world. We adapted that to the automotive use case to provide a very robust, high-speed, long to carry things like Ethernet, USB controls, audio. And that chipset actually has achieved great success. We're on the road now for 2.5 years with Mercedes-Benz, providing the wired connectivity backbone for their MBUX infotainment system. So we've had, it started off with the S-Class, it's now moved throughout the range. But then we also adapted that technology to be the basis for the new MIPI A-PHY standard. So what happened was the MIPI Alliance wanted to create a physical layer interface, a SerDes solution, serialized deserialization solution, targeting the automotive industry. We went and proposed our technology, that same technology that's been on the road with Mercedes now for a few years, as being the best solution, and other companies proposed other solutions. And after, I think it was about 1.5 years, 2 years of discussion and debate at the MIPI Alliance, they decided that the Valens technology, that our approach to this was the correct way. And we are now the baseline technology for the MIPI A-PHY standard. Of course, they modified what we had done as part of the standardization activity. But the fact that it's based upon our technology gave us the benefit of understanding it probably more than anybody else to begin with, and gives us the first to market benefit as well. And what this means is that what we're showing here at the show is our first generation of A-PHY compliant chipsets, the world's first A-PHY compliant chipsets, our VA7000 family of devices that bring finally what the industry needs, a standardized, high-speed, long-reach, ultra-reliable SerDes technology for the automotive industry.
So Daniel, I'm going to ask you to be a professor, and I'm going to be the student, because there's a few things I want to pick your brain on, just so that I can learn and get a better understanding. So, and I'll refer to my notes here, the need for standardization. You mentioned high-speed SerDes data. So the need for standardization, high-speed SerDes data link for sensor connectivity. Walk me through this. Give me the 101 lesson on this.
Okay, so first let's talk about the standard part of that, what you have just said. So a standardized solution. For years, other MIPI standards have been deployed in vehicles, things like CSI interfaces for cameras and DSI interfaces for displays. But the M in MIPI stands for mobile, and MIPI began its life as an organization that was standardizing interfaces for our cell phones, which have cameras and displays, of course. But of course, our cell phone is this big, which means that the interface needs to drive a distance of a few centimeters, a few inches within our cell phone, whether it's from the camera to the processor or from the processor to the display. Now, when those interfaces, the CSI, DSI protocols were taken into the car, a few inches is not enough. You need tens of feet, So what happened was sprung up certain single source proprietary analog SerDes technologies that could extend from a few centimeters to the tens of feet that are required.
Yes.
However, proprietary and single source, as you well know, are not words that the industry likes.
Yes.
In particular, given all of the supply chain issues that have been experienced in the semiconductor market over the past few years, targeting specifically the automotive industry.
Right.
So what the standard now brings you is a solution that is put together by the MIPI Alliance, which I should mention has some 400 member companies, around 50% of whom are already in the automotive industry.
Right.
And now has standardized an interface designed from the ground up to be suitable for automotive. So in other words, it's designed to handle the distances that are required, the bandwidths that are required. It's designed also to handle the strict EMI, electromagnetic interference, electromagnetic compatibility requirements that the industry places on such data links.
Right.
And now we have it standardized. I'll mention as well, MIPI developed the spec, but so good is A-PHY that just 3 weeks after Spec 1 was announced, then the IEEE, another huge, of course, standardization body, also announced that they were going to be adopting A-PHY as is.
Right.
So it's now a MIPI Alliance standard. It's now an IEEE standard, IEEE 2977. So we have these two huge standardization bodies throwing their weight behind the standard.
Right.
Standardization means ecosystem, right? We've seen it with Ethernet,
Yes.
And now we have a standardized solution and an ecosystem of vendors that can play in that space, or providing technology that now interoperates.
Right.
So Valens are the first to bring A-PHY products to market, I've said that, but others are catching up. We've heard public announcements, for example, from Sony Semiconductor Solutions, I believe the world's #1 sensor vendor, who have already announced that they are integrating A-PHY directly into the sensor. So that means in the camera, you won't actually need the serializer, the transmitter chip at all.
Right.
What does that mean? Smaller camera, less power, less heat to dissipate. And standardization brings that possibility. Integration is only possible when there's a standard, because it's open to anybody who has access to the standard. Okay.
That makes sense.
So then we have this standardization element, but then we have the technology element as well. Okay.
Follow you.
So A-PHY brings you very high bandwidths with extremely robust data links. By high bandwidths, I mean the first two versions, Spec 1 and Spec 1.1 of the spec, give you up to 16 gigabits per second in the downlink.
Right.
So when we're talking sensors, we're talking about 16 gig of data coming from the sensor to the ECU that needs that data to process it. In the uplink, we have, depending on spec, either 100 meg or 200 megabits per second.
Right.
So it's a highly asymmetrical data link, which is exactly what you need for sensor connectivity, right? Because, of course, as I've said, a ton of data goes from the sensor to the processor, and all that's required is low bandwidth data just for control, management, monitoring.
Right.
So we have a lot of bandwidth available to us. Our first generation of product, I'll mention, handles up to 8 gigabits per second in the downlink. A lot of bandwidth, very, very low latency. And we're talking about things here at AutoSens that are now mission critical, right? The driving is being taken from the hands of the driver and being passed on to the compute elements within the vehicle.
Right.
Latency becomes a critical element. Latency means the delay between the transmission coming across the data link, okay? The longer the delay, let's assume it's, for example, an autonomous braking system, the longer the delay, the longer it's going to take to bring the vehicle to a halt, right? And A-PHY specifies a fixed latency at 16 gigabits per second of only 6.5 microseconds, right? That, to all intents and purposes, is zero latency.
Yeah, right.
So at a system level, the system that requires that data experiences no delay on it. So we've got a lot of bandwidth, we've got no delay. But those things, the high bandwidth as a general rule does not work well in automotive because of the electromagnetic noises. The higher the bandwidth, the more the impact of the electromagnetic noises in the vehicle can have on the data running in the link. Those noises can come from the spark plugs in our ignition system. They can come from the wiper motors, the window motors. With EVs, it becomes even more complicated because you have huge currents flowing through the vehicle that are basically radiating electromagnetic noises in the cables that they're in. So how do you bring together the need for high bandwidth with the strict requirements of the automotive industry in terms of EMC? Legacy analog SerDes solutions, first of all, they do that in two ways. They avoid the noise. And how do they avoid the noise? One, they limit the bandwidth, okay? Less bandwidth means the noise will have less impact on it. They also reduce the cable length, and they have to work with shielded cables. Shielding is a metallic braid around the cable that protects it from noises coming into the cable or going out. But that limits architectures, that imposes costs. The cables are expensive, the connectors, shielded connectors are very expensive. And A-PHY has a completely different approach. Rather than trying to avoid the noise, A-PHY says, okay, will accept the noise, will learn it, and will cancel it out. So we have mechanisms, hardwired DSPR mechanisms, digital signal processing mechanisms within the chip that allow us to learn the noise and to get rid of it. And even though the noise transmission then continues and the noise interference continues, the data now passes through the link completely uncorrupted by those noises.
That is cool.
We can do that up to 4 gigabits per second using unshielded wires, which is unheard of in the industry, to get such high bandwidth without the need for shielding. We have mechanisms in there that allow us to retrain the link, allow us to recover any corrupted data packets while that cancellation was occurring. We use something called PAM, pulse amplitude modulation, that reduces the frequency of the data in the cable while maintaining high bandwidth. Lower frequency means less losses in the cable. Less losses means a longer cable, a simpler cable. It also means with less losses, you transmit at a lower power, so there's less radiated emissions as well. So we have all these goodies within the PHY, within our DSP mechanisms that allow us to run high bandwidth, long cables with beautiful EMC performance that has already been tested. But in Japan, for example, has been, and this is public information by JASPER, which is the umbrella organization of the entire Japanese automotive industry. They already took this A-PHY technology from using our chipsets, and they tested it for EMC compliance, passed first time. There's a report on their website you can download. So we've kind of got the holy grail here: high bandwidth, low latency, extremely robust in the electromagnetic noise environment. It's like the perfect storm for exactly what the industry needs now in terms of their sensor connectivity.
It's just incredible. My mind is just blown.
It's a great technology, man.
It's unbelievable. I've got more questions for you, but as an aside note here, when we do audio production for AutoVision News or like video production, and you get into a program like an Adobe Audition, you have noise filters where, again, you filter out the background noise, you filter out, the stuff that's not pleasant to the ear, but the waveform still goes on. And you're talking about, you cancel out the noise, but then you still go on business as usual. That it's very similar to the like audio production work we do.
And if you think about sorry to interject there, but if you think about it, when I now get error-free data in my processor, my processor has to work less hard, because when it's getting data with errors, it now has to find a way around correcting those errors. Just like you said, Adobe are doing this. But now I have a real-time processor that's handling all the sense information on a mission-critical, safety-critical application within the vehicle. And suddenly I've simplified the work that needs to be done to clean up the data that's coming in, because I'm guaranteeing clean data into that processing unit. Take away the noise, it needs to work less hard.
This is awesome. Like from a benchmark engineering perspective, the benchmarking, this is so cool. MIPI A-PHY. Okay, so I'm back to being the student again. You're the professor. What is MIPI A-PHY? I know we've touched on it a little bit, but what is it? Tell us about it, and we'll go from there.
So we're talking about SerDes technology: serializer, deserializer. We can look at that as transmitter. That's the serializer. Receiver. That's the deserializer. In its current form, 5 gear speeds are defined: 2, 4, 8, 12, and 16 gigabits per second. Gears 1, 2, 3, 4, and 5. The technology is very smart in how it drives the signal into the cable, because A-PHY changes the modulation scheme, which is the way the data is transmitted. The number of levels of data that are transmitted at any point in time changes according to the gear that we are in, the link speed. Now, it can be NRZ, which is like a 2-level signaling. It can be PAM4, which is a 4-level signaling, or PAM8, which is 8, or PAM16, which is 16 levels of signaling. And why is all this important? Because it comes back to what I said earlier. It comes back to keeping the frequency of the data in the cable low. So what happens is, as we go up through the bandwidths, through the gears, we change the modulation scheme to transmit more bits each clock cycle. The effective meaning of that is that at no point, right the way through to 16 gigabits per second, will I go above 2 gigahertz frequency on the cable. So there's frequency and there's bandwidth. The frequency is what dictates the losses in the cable. So, but by changing the modulation scheme and keeping it up to a maximum of 2 gigahertz, I maintain low insertion losses and return losses in the cable, right? And as I've said, this is very important because it reduces the cost of the cable. I can use cheaper cables, I can use longer cables, cheaper connectors, and I transmit with lower power, meaning I radiate less emissions. So it's a very, very cool modulation scheme that legacy analog SerDes don't have, right? So in other words, for them to get more bandwidth, they need to jump their frequency much higher. To get to 16 gigabits per second with a legacy analog SerDes, you need an 8 gigahertz frequency, and that is a hugely lossy input into a cable.
Right.
So we have this goodness going on in there that maintains the fact that, yes, we keep the frequency low, we keep the losses low. We keep the radiation low. I've talked briefly earlier about the noise cancelling.
Yeah.
I talked about retransmission mechanisms that happen at the physical layer, ultra-fast retransmission to recover any corrupted data packets. And when you put all of that together, what it gives you is a packet error rate of 10 to the minus 19. Now, maybe not everybody appreciates the value of that number. First of all, it's orders of magnitude better than existing solutions today, but somebody who's much smarter than I am can do the maths that I certainly can't do, said that if you were to use a car for a typical number of hours a day, packet error rate of 10 to the minus 19 means one packet error, something like every 70,000 years.
Yeah.
Okay, so it's hugely robust. And again, all of this within an environment that is extremely electromagnetically noisy, right? There's almost nothing worse than an automotive environment.
Right.
So high bandwidth, EMC robustness. As I said, it's a great technology, and we're proud to be the first to bring these products to market.
Daniel, let me pick your brain on radar architecture. So what sort of architecture changes then can MIPI A-PHY enable when we're talking about radar?
Great question. So today, and radar is one example, and I could probably equally apply this to LiDAR as well, and maybe some camera technologies. But radar today heavily relies on what is known as edge processing.
Okay.
So what happens is, within the radar that's fitted to the physical envelope of the vehicle, you have the radar chip. It's called a millimeter wave IC, or a MMIC, and that's actually the brains of the radar. That's doing all, the sending and the receiving through the antennas of the radar data to get the radar reflection back. Now, the data that comes off that MMIC chip is raw data. It's a CSI interface, which is another MIPI standard. And what they are doing now is processing all of that raw data in the radar. Okay, so they have a big, hefty processor within the radar. They take the raw data and they crunch it up. And let's look at it as though it's a compression of the radar data.
Okay,
And they do that in order to have low bandwidth link data that they can send over a low bandwidth link, maybe a low bandwidth mega Ethernet link, or even something like CAN-FD, down to the processor. So I have very high bandwidth being crunched down and compressed to low bandwidth being received by the processor.
Got it.
What's the problem? So, I mean, it works, but it's definitely not optimized. Why? Number one, I'm putting a fairly hefty processor unit inside of the radar, which means the radar needs to be physically bigger. Of course, that introduces cost. That's a processing unit in a radar, and there's multiple radars in the vehicle. That's a lot of cost going into each and every one of them.
Yes.
Because it's power hungry, I now need a separate power line in my harness. I need an extra power connector on my radar. When we talk about the future of software-defined vehicles, that this is this buzzword that's going around. You cannot have processing everywhere, right? Because it's impossible to maintain over-the-air updates. If I have to update every single unit, there needs to be a move to centralized processing. And here, every radar's got its processor. And the final point is, of course, because I'm now crunching data, and you come from a video background, so you understand what compression does to an image.
Absolutely.
It's not the same image. So the data is compressed, it's crunched, and the ECU receiving that radar data suddenly doesn't get a particularly great impression of what's going on. It's not terrible, but it could be better.
Yes.
And what MIPI A-PHY and our VA7000 chipsets allow us to do is break that architecture apart. So what we now have is a lean radar for centralized processing. What do I mean by lean? Throw away the processor in the radar. Take the raw data that's coming off of the MMIC chip, drive it untouched into our A-PHY link. So as our A-PHY transmitter chip, our serializer, receives that CSI traffic without any data being lost, sends it across a link, which is highly robust, no bits are lost, and now the processor is receiving raw data. And it can get that from various, multiple radars around the vehicle. And now we have a kind of a lean radar with a central processing. What does that mean? The radar is smaller. We have on our booth a radar from a company called SRS. They're smart radar systems from Korea. They showcased the SRS, one of these lean radars. They told us it was a quarter of the size of their existing radar. It's much smaller. It needs less power because there's no processing done in it. So what happens? They can use the same cable for the data that comes from the radar to the processor also to drive power and power the entire radar itself. It's smaller, it's lower power, it's cheaper. And because now this central processor over here is receiving raw data, the perception that it gets is much, much better.
Right.
So it's like, you're providing it fully, every bit of data that the radar mimic chips are receiving, being processed, centralized, and it gives them a completely new approach to this radar architecture.
Right. Daniel, this is so cool. I mean, where do you go from here? I mean, you're talking incredible innovation already.
Sure.
Where do you go from here? What's next in your product roadmap? Like, how do you top this?
It's a hard one, that one, and again, I need to be a little bit careful what I share in this kind of environment. But listen, as I've mentioned, our first generation of chipset goes up to 8 gigabits per second, but I've already stated that the first two versions of MIPI A5 Spec 1 and 1.0 support up to 16 gigabits per second.
Yeah.
So you can imagine where we're going with this, okay? That the sensor resolutions are increasing, the bandwidth requirements in the vehicle are going up. Yep. So we are, let's say that's where we're heading next, okay? Yep. So we appreciate that that's where the industry is going. We have the technology. I can tell you we already have a test chip running, at least like the analog portion and some of the digital signal processing that we have running at those 16 gigabit per second link speeds.
Right.
And now we just need to productize it. So I'm not going to tell you, of course, a timeline in this environment and exactly what that product's going to do beyond that. But yeah, we see MIPI A5 because it is such a robust technology, because it is designed from the ground up to be for automotive, because it is a standard with a very rapidly emerging ecosystem. We definitely see that as being where we need to be pushing our product range to support the industry and its needs.
Yeah, I'm excited for the near future here for you, Daniel.
Thank you.
Is just as far as the industry overall, what is on the horizon as far as trends? What do you think we should be paying attention to? What do you think we should be aware of as we go forward?
Wow, there's so much, right? There's so many trends, and it depends who you speak to. I've said it here, I'll say it again. I mean, it's about the bandwidth, right? Yeah. The movement from level 2 plus to level 3 and then beyond is going to need a change in their vehicle architectures. Distributed architectures, I think we can all agree, are pretty much behind us now. We need to move to something that's more lean, more streamlined, zonal architectures, centralized processing architectures, in order to take the ton of data that these vehicles, these higher level of autonomy vehicle, ADAS and eventually full autonomy vehicles are going to need. We're going to need to move all of that to a few centralized processing units. You need the data links to be high bandwidth, robust, resilient to those noises, low latency, and we give all of that. I think the challenge may be on the processing side, right? Yeah. And I mentioned this yesterday, actually, in a talk I gave, that suddenly you're going to have very high power demands of the central processing unit. Yep. So there's going to be a lot of activity done by those guys to reduce the power. But I heard from a very well-known research organization, he said they're updating all of their forecasts suddenly because the move to centralized processing is coming faster than anybody thought. Yep. So that's a whole other aspect of the discussion, but we're there to provide all of that high bandwidth, low latency, robust interfaces into the centralized processing. I think that's where things are heading. I can't
wait to play this interview back and listen to this again. Daniel, thank you for thank you for the lesson and the lecture, letting me be the student. You being the professor. Helping me get my mind around this. And for all of our AutoSens viewers, Daniel is tagged as well as Valens, both tagged in the post that accompany this video. So please reach out to Daniel to learn more. In the meantime, I look forward to doing this again and discussing the latest innovations. But in the meantime, have a great rest of the show, Daniel. Safe travels home.
Thank you,
and I'll look forward to our future discussion.
Likewise. Thanks so much for having me here again.
Indeed. More to come from AutoSens Detroit here on the AutoVision News LinkedIn page from the Huntington Place in downtown Detroit. I'm Carl Anthony, AutoVision News.